Proof by cases. Now, this sounds pretty good at first. I'm not going to argue that. And it's a little bit simpler on the overall setup. But what's going to happen is to prove a conditional statement with several P's in the form of, remember you've seen this before, where we've had several different items that are in our P portion of our propositional logic and hopefully imply a specific Q. Now, where each Q is treated as a specific case is what we're about to start doing. With that thought, we can use a tautology to our advantage. How's that? Well, think of it. We're thinking of each of these are or symbols, so we're thinking this one or this particular case. Then we can end up having our implies Q. But what we can do is we can swap things around, but this time it's using an and. These are equivalent to one another. We have one particular case and see if it implies Q. Another particular case implies Q. But the important part is it has to be an and. So all of these have to be true in order for, well, frankly, the proof to be true as well. We only need one of these to screw this up. One case that ends up false means the entire proof is false. So that's what we have to check out for when we do this. There's two different setups when we do this. There's the P implies Q, and then there's the multiple variables, which we've talked about before. It's P or Q, implies R, and we've talked about that as well. So when we're dealing with just a normal P implies Q setup, all the cases, we have to set up all the cases for all possible scenarios. We have to make sure that we denote the domain. Is it an integer? Is it a whole number, etc.? For each of the variables, we're going to conduct each case. To be honest with you, we can be kind of short on that too, meaning that what if we happen to find a false? Then we're done. That's all we need. But if all agree with Q for all cases, then we're going to have, therefore, using proof by cases, it is true. So that's the overall setup of how it's going to look. Here's a proof by cases example number 1. Prove n is an integer, it's a P portion, and n is either going to be less than or equal to n squared, and that is our Q portion. All we're doing is basically listing out cases. Now, the cases are being highlighted right now, but to save some space, I did the ... there. So n is less than or equal to 1, n is equal to 1, or n is greater than 1. So this is all possible cases because n is an integer. And by the way, it really doesn't specify, no, it says integer, so that would be z, and remember our z symbol for integer includes 0. So that's why we have to include all three cases of 0, greater than 0, and less than 0. Now, all we're doing for each case is going to test it out. Because frankly, the first part is therefore it is going to follow because it's going to be true because a negative times a negative, because we have a negative 1, negative 1 squared, which equals 1, is a positive and true for that particular condition. So notice all I'm doing is basically plugging numbers in that we have right here and then proving if it's true or false. Now again, we have the 0 part. 0, now I got to be careful. 0 squared is equal to or less than or equal to 0. So that's still true, and then obviously the other way around is true as well. So we have since n is less than or equal to n squared for all values in the domain, we can conclude what we've got is true. So to be honest, I would add one more thing to the basic conclusion line here. I would state that proof by cases, or using proof by cases, since the rest of it, just to let me know what you used in order to solve that, so we can kind of formulate in our head what game plan that you wanted in order to solve this. This one is also from the Rosen book. So the setup is a little interesting here. Let A at B equals the max of AB, and A if A is greater than or equal to B, otherwise A is A at B. Now you know why this is going to be tougher for me to demonstrate, or not demonstrate, but go over here. So what they're trying to do is they're basically trying to prove all of these conditions to see if then one of the following cases must hold. So to start off with, I basically set, hey, A, B, and C are arbitrary and they're real numbers. Then I come up with all of the different scenarios that we can have for A, B, and C. So notice A's got two different scenarios where it starts off, B does. Notice if we did a truth table, it would look very similar to that. So that's why it's laid out that way. Also, to be honest, the book only goes over one case, but it basically is trying to tell you, hey, this case ended up to be true. I should go on to case 2, 3, 4, 5, and 6. And it says, but a complete truth will require that the equality be shown for all of those in all 6 cases, and the proofs for remaining cases are similar to what we had here. So in reality, even though this is straight from the book, the author didn't go through each case to prove each one, but each one of them ended up to be true. So that's how we can get away with basically proving that this particular theorem is true, by using proof by cases. This one, frankly, I like a little more. We're given an equation. If n is an integer, that's p, then n squared plus 3n plus 2 is even. That's our q portion. So what am I going to do? N is an integer. You've seen this before. N is even, n is equal to 0, n is odd. That looks pretty familiar. Now, to be honest with you, I wanted to show all the work, so otherwise it's not as flat as the previous one. But I wanted to show you all the work on getting everything done and situated for that. So you'll notice that n is even. That 2k showed up. N is equal to 0. I used direct substitution, put a 0 in there to solve that out. And n is odd. I'll be darned at 2m plus 1. I'm not sure why I used m in this case instead of k, but it doesn't matter. The variable letter doesn't matter. But notice, hey, there's my setting things up. Up there is my substitution of 2r, which makes that even. That's right. So in case number 3, if we're presented that n is odd, we go ahead and set things up. But notice again in our q portion, it ends up being, well, even again. We have 2l, where l is all this stuff, and that means that's going to be some type of even with it. So that's where it follows. It happens to be true. Q ends up. So each one of these, Q ends up being true. So since then, or since the equation is even for all values in our domain, we can conclude using proof by cases. I would still add that somewhere in there. For all values of n that are in there are integer, then our equation is equal to even. It's equal to even, is even.